Welcome to everybody in this remote session. As Ian said, of course, feel free to interrupt me, ask questions, of course, if they are urgent and of general interest, because we have 2 hours, so we can have a large discussion during the course, and then we can, of course, have more, how to say, deeper discussion at the end. In principle, I hope that we will have 15 minutes, even more, if we want, for the discussion. So I'll start sharing my screen with the presentation. All of you have received the PDF of the presentation, so that probably you can follow even better, and maybe you had already looked, and to help you to, yes, to make your mind, because we are going to go in these 2 hours in a high-speed velocity, high-speed train, because I have to tell you a lot of things. I'll try to be as clear as possible, but as I said, if I'm not, go ahead, interrupt me. So there are 2 parts for this the today lecture, and in between we will have a 10 minutes break, so we can breathe. In the first part, I will introduce briefly the ISM, and then in the second part, I will give you some information about the molecular clouds and up to the star-forming region, without really touching the star-forming regions, because Paola Caselli will take care of it. So let's start with the ISM. This is the outline. And let me first say what is this ISM, that is for Interstellar Medium. You see now these beautiful pictures that show this galaxy on the right and the cluster of galaxy on the left. And this is what makes, at least certainly for me, what made astronomy so fascinating: the stars in the sky, the luminous matter that we see in the sky. And now we know that even though this is probably what pushed, I hope, many of you to do these studies, to do a PhD in astronomy, this luminous matter actually represents a really ridiculous fraction of the whole matter of the universe, less than 0.2% of the matter of the universe. Where it is how we know that this is the case? Of course, this is because we have a number of observations that have been carried out for decades, and the last one is the one from the European satellite Planck on the cosmic background radiation about 10 years ago. And if you interpret this data through a cosmological model, this is very important to keep in mind, then we have the distribution of the mass budget of the universe in the figure on the left, in which you see that the vast majority, 95% of the matter, actually is part of the so-called dark sector, dark matter, dark energy, that we use the adjective dark because actually we don't know what it is, but still, being astronomer, we are not discouraged, and we are not, how to say, too ashamed to say that. Now, let's focus on the baryonic matter then, that, as I said, is the ordinary matter that forms stars and humans, and that is only 5%. Even for this 5%, you see on the right the camembert, that is the distribution of the matter, of the baryonic matter, and again, stars, that is the real luminous matter that you saw in the picture, represent only 7% of the baryonic mass. 64% are in a diffuse state, different state, and then again we have about 30% of baryonic mass that is unaccounted for. We don't know where, why, and what constitute this dark baryonic matter. In this course, of course, we will focus on the cold gas, that is only about 1/3 of the luminous matter, but as we will see, of course, of extreme importance, actually for the shape of the galaxy, certainly for the next birth of the stars. An obvious indication of the presence of the interstellar matter are the dark lines in the Milky Way. When I know that from here it's not easy to see them, but we now have the internet picture and so on, and you see on the right figures, indeed the galactic, the Milky Way toward the galactic center, but you see that there are these dark lines that is not a region where there is no matter, okay? But there is a region where the matter is cold, and it is between us and the background stars that make the luminous appearance of the Milky Way. It is even simpler to see this ISM in galaxy that are not the hours, like for example in the picture on the left, in which you have the Andromeda galaxy. On the right is the luminous with these black bands. And exactly where you see these black bands, there is emission on the left of CO, which is a proxy of this dark, of this cold molecular interstellar medium. Actually, is a proof of the molecular cloud, the molecular clouds. The presence of the ISM has been known now for almost 1 century, even though it was understood the real nature much later, because at the beginning it was thought that there were really holes in the space in the galaxy. Now, before we go ahead with the ISM and the physics and what we know about it, one important and even extremely paramount importance is the abundance of the elements, because after all, the ISM is what it is because there are the quantities and the numbers of elements that constitute it. And so very briefly, I just remind on the left, I put the table with the abundances of the major elements in the ISM close to the sun, and remind very, very quickly the origin of these elements, because it's important to understand what I will say later. As you know, the light elements, that is the hydrogen, helium, and their isotope, were formed in the first 3 minutes of the universe in the primordial nucleosynthesis. And actually, it is based on these abundances that we know how much baryonic mass exists. Then there are the intermediate elements that are lithium, beryllium, and boron, that are due to spallation reaction, so caused by the cosmic rays. And then we have the heavy element that carbonium, nitrogen, oxygen, and then silicon, sulfur, and so on, that are formed in the interiors of the stars. These are also called metals by astronomers. Something that when you meet a chemist, if you want to cause an infarctus, you tell that carbon is a metal. Anyway, this heavy element abundance depend on the number of the previous star generation. And therefore it means that these abundances, and that's the reason why I specified that these are the abundances in the sun neighborhood, these abundances depend on time and space, and even in our galaxy, where we are with respect to the galactic center. But these are numbers that are absolutely important to understand the physics and chemistry of the ISM, and it is as it is exactly because we have these numbers. In general, these elements are, where are they? They are in gas and dust. And gas and dust in the ISM are very few exceptions mixed. So when I say gas, what do I mean? I mean hydrogen, of course, and then helium, which is a noble gas, so it's always like this, and then small quantities of heavy elements such as oxygen, carbon, and nitrogen. And the gas can be ionized, atomic, or molecular, depending on the status of the hydrogen atoms. Why? Because as you see in this table, the most abundant, apart the helium, that as you know is a noble gas, so doesn't care, let's put it this way. The most abundant element is oxygen, and it is more than, is about 2,000 times less abundant than hydrogen. So when one think of the gas, think of the status of the hydrogen atoms. Then there is another component that is the dust. What is the dust? They are really small grains of solid material, basically silicates or carbonaceous grains, and their average radius in the Milky Way is about 0.1 micron, and we will come back on this number. What is important, extremely important to say, is that the total dust mass is about 100 times smaller than the gas mass. And this is a nice exercise that I suggest you to do if you haven't already done during your courses. If you assume that the dust is formed by silicate with magnesium and iron, what would be the largest possible silicate dust-to-gas ratio mass? This is a simple and nice exercise that shows that we have a problem, and I encourage you to do. Anyway, despite this relatively small mass, dust has an immense impact on the physical and chemical status of the ICM, and that's the reason why I will spend some slides on this, on the dust, actually, because it has all this impact. Anyway, before talking about dust, let's give an overview of the interstellar medium. And again, in this case, the phase of the interstellar medium are characterized by the status of the H of the hydrogen, which is the ionization, density, and temperature of the hydrogen. And this table provided the approximate characteristic of these phases. There is the hot intercloud medium, the warm ionized medium, warm neutral medium, cold neutral medium, with the characteristic that you see in the table. So it goes from 1 million degree for the hot intercloud medium up to about 80 Kelvin for the cold and neutral medium. Let's be clear, the hot intercloud medium as well as the warm ionized medium are both ionized. The first one, by definition, being at 1 million, the second one because also has a temperature close to the ionization, but in this case is really ionized. Then there is the famous warm neutral medium and cold neutral medium, in which the hydrogen is neutral, so it means it's atomic. And in this case, in the warm neutral medium, we have 8,000 Kelvin, while in the cold neutral medium, we have 80 Kelvin. And the densities goes from 0.5 for the W and M to 100 times larger for the cold neutral medium. And this is not by chance, because these two phases are in pressure equilibrium and are practically coexisting. Anyway, there are the H2 regions that are the regions around, in general, all B stars that are ionized by the photon emitted by these stars. And then there are the molecular clouds that are the densest and coldest part of the galaxy, and whose mass is about 1/3 of the neutral molecular cloud medium. Okay, what happens to the ICM? And this is obviously important. As I said, here is a scheme of the formation practically of the elements. But let's start at any point on this loop. Let's start for a diffuse cloud. The diffuse cloud, as I said, could be a neutral medium or even the ionized. And then if nothing keep the cloud hot, it will slowly cool down, and if it cool down, becomes denser, and depending, of course, on the total mass of the source of the cloud, it can become a dark cloud, a molecular cloud, inside which there are the stars that are formed, and then depending on the mass of the future star, there will be massive or low mass protostars with a knot core for a massive protostar, and not Corino for a low mass protostar. And what happens then, the fate of the material is slightly different, but not so much. If a massive star is formed, then it will end up to be exploding as a supernova, so that the elements that have been synthesized in its interior are ejected in diffuse clouds, which means in the ISM. If it is a low mass, the route is slightly different. It goes for a disk, for a planetary system, whatever. It lives longer, but then it will die eventually. And also in this case, because of the wind that come out from the AGB stars. Anyway, the material that has been synthesized in the interior of the stars, a part of it, of course, will be reinjected in the diffuse clouds, which is in the ISM. So you see that there is a loop, and you see, you understand immediately that there is a feedback between star formation and the ISM, that the two are absolutely interplayed. The structure, composition, chemical evolution, observational characteristic of the ISM depend on the star formation rate, and vice versa. So, and that's the reason why one cannot study star formation without understanding at least having a general understanding of the ISM, and vice versa. Studying the ISM without understanding having a general understanding of the star formation is the same, is impossible. So let's move now to the interstellar dust, and in this, say, 15 minutes or what. So, as I said, the interstellar dust in mass contribute to a very small amount, around 1/100. But yet, it plays a huge role in the physics and chemistry of the ISM, in particular in molecular cloud, because I will really focus on molecular cloud. Since dust absorbs photons much more efficiently than the gas, it is the dust that is responsible for the absorption of the UV photons. And as you know, the UV photon destroy molecules and also the H2. Therefore, by definition, is very important in molecular clouds. And then the second reason is that dust provides the surface for some extremely important molecule formation. And I will provide a few examples a bit later. needless to say, but better to say, we do not have a sample of interstellar grains in our hands. So we cannot study in our laboratory what are really made of this interstellar grain and the structure and so on. Everything that we know because we interpret the astronomical observation through experiences, laboratory experiment, and understanding how the dust grain absorb, scatter, and emit photons, which is the things that we receive that we really have. And here you have the three figures are meant to show you these three major processes of dust. On the left is absorption of the absorption caused by this cold cloud that is black, which is especially the absorption from the dust. Then in the middle figures, you have this diffuse blue emission that is not because the gas is white, but just because the dust scatter the light from the stars. And then on the right, you have the image of the map of a cloud, a molecular cloud, emitting photons, obviously not in the visible, but rather in the millimeter because of its low temperature, but we will see it a bit more in detail. So the first thing to remind, in case you don't know, I guess you do, but let me go very fast, is dust is measured or what we receive of the dust is the first thing, in fact, the first quantities that characterize the dust, the interstellar dust, is the absorption and the reddening effect on the light of the background stars. The quantity that measure this dust absorption is called extinction and is a function of the wavelength. The function of the extinction function is the extinction as a function of the wavelength, the inverse of the wavelength is in the figure on the right. And what should I say? And then there are historically two other quantities that you certainly have encountered, or you will, that is the reddening, that is the differential extinction in two wavelengths, and then the total to selective extinction ratio that is measured in the B and V in visual, yes, blue and visual wavelengths that is given by the extinction in the visual divided the reddening between the blue and the visual. Now, why I introduce all these quantities? Because if you look now at the curves in the figures on the right, you can see that these are observation, is not, and then with some models, but the dashed curves are observation. Wherever you look in the galaxy, any direction practically, you always have the same picture, that is the one that you see. The only difference is a sort of how to say, scale factor that is given by this RV ratio, that for the diffuse warm ISM it's about 3, while in molecular clouds varies between 4 and 6, but this is very difficult to say because molecular cloud, by definition, you don't have really the extinction in the visible or in the ultraviolet, obviously. But this is therefore derived for the molecular clouds with a small column density, that is small molecular clouds. Important, and I'm pretty sure that you know, there is a relation between the visual extinction and the total column density of the gas in the line of sight. total column density means the column density of the atomic hydrogen plus twice the column density of molecular hydrogen. And which practically is the observational relation that tell us that dust and gas are always mixed, because otherwise extinction, being a measure of the absorption of the dust, is a measure, it should be a measure of the column density of the dust. The fact that we see observationally that there is a relation between the extinction, the visual extinction that is linked to the dust column density and the gas column density, and these are observations, tell us that dust and gas are always mixed and their ratio is always the same, this famous 1/100, that, by the way, comes exactly from this relation, not from the abundance of the elements. If you do the little exercise, you will realize you will have fun. Okay, this structure, extinction structure, provide us with a huge amount of information of the nature of the absorbing material, is a mineralogy and size. Is there really the major information that, if not the only one, that we have to say what this dust is made up. Let's start with this bump at 2174 angstrom that is shown by the red arrow. And that is a characteristic of an absorption associated with the resonance of a conductor, probably carbon-bearing solids. Be aware that the extinction is absorption, okay? So it means exactly that. So in increasing absorption, in the extinction curve means in increasing absorption. So there is something that is particularly efficient to in absorbing the 2174 angstrom photon. And this based on our knowledge of solid material, and of course also the elements abundance on the SM is very probably carbon-bearing solid. So it is grains made up of carbonaceous material, which means that the basic structure is graphite, but we don't have more information than that actually, because this is very little, how to say, defining this in this term, this bump, and we'll see why. In fact, I say that in the next slide as comparison with the silicate. And for example, this feature could be also fit very well with hydrogenated amorphous carbon, which is small, again, pieces of graphite, but with about 30% of hydrogen mixed up. And to understand how much of the carbon should be locked in dust, in dust grains, we use experiments that we do in the laboratory on an analog of what we think could be this carbonaceous grain, and it turns out that a big fraction of carbon is probably locked in these grains. You see, I put a number of 6×10⁻⁵ carbon atoms if it is only graphite, but if it is amorphous, hydrogenated amorphous carbon, it could be twice larger. We don't know, because with this feature, it's really very difficult to give a strong constraint, but keep in mind that an important fraction of carbon, elemental abundance, is indeed trapped in the dust grains. And then, of course, we have other means to say that. The situation is a bit better for silicates, because silicates, we don't have just one bump that could be caused by an entire class of solid material. We have two specific bands features at 9.7 and 18 micron that identify very precisely the mineralogy of the carrier of these two features, and they are olivine and pyroxene. The basic structure of olivine is shown in the right figures. So there are 4 oxygen with the silicon inside, and then this is in a tetrahedra. And in between the tetrahedra, there are magnesium or iron dispersed. And this, the relative strength of the two features and the depth also provide a lot of information now, not only on the composition, so if there is more iron, magnesium, etc., but on the thermal history, the size, the geometry of the grains, whether they are spherical, oblate, if they are fractal, and everything is derived, of course, by comparison with the terrestrial experiment that try to reproduce what we have in mind as an analog of the dust grains, but obviously, by definition, cannot really reproduce the interstellar dust. We don't have them it in our hands. So everything has to be taken with caution. We are astronomers and we live far away from the object that we study. Another important information, especially for the now when we look through molecular clouds or dense cold object, this infrared spectra present many features due to frozen molecule. Because in this case, you have really bands. Each band corresponds to the vibration of a specific molecule, and that's the reason why we can identify very precisely what is in this solid status. The comparison with laboratory measurement tells us that these dust mantles are mostly constituted by water, and then in a fraction that is about one third, depending on where we are looking for, there is CO and CO2. And then there are other complex molecules that also have been identified, like methane, ammonia, and methanol. And what we think is that this ice molecule envelop the dust refractory cores that are the carbonaceous and the silicate in molecular clouds, like represented in the figures on the right. And then what is important to realize is that the different dust mantle composition is an important source of information of the history of the molecular clouds, because it depends on it, and affect enormously the chemistry in the protostellar object, which means also probably the chemical content of the future planets that will be in the planetary system Okay, I said that the average radius of the interstellar dust grain is about 0.1 micron. Where does it come from, this number? There are various ways to estimate the grain radius, the grain size distribution. One is exactly the form of the extinction, because we see that dust grains absorb from the infrared to the far ultraviolet, so which means that there isn't only one size of the dust grains, but there is a span of ranges, but a range of sizes. And then once one has identified the mineralogy, the grain component, that is silicate, graphite, HAC, using the optical properties measured in laboratory, comparing again the shape of the extinction curve, one can give also a grain size distribution. Of course, there are people that just work on that, and things can be extremely complicated, as you probably know. The most popular and widely used model is the so-called MRN, by the name of the three persons that first proposed it. That is, after all, a quite good fit of the diffuse interstellar dust, which is that the number of grains with a given radius is proportional to a power law proportional to the radius to the minus 3.5, of course, with two limits. That is about 50 angstrom and 0.25 micron. But there are regions in the ISM in which the grain could be smaller, for example, where violent shock can shatter a fragment, the dust, or larger, for example, in interstellar core protoplanetary disk, and certainly you will hear by Paola about that. And I think that I have finished the first part, which is amazing. I thought I wouldn't make it, so I can take questions if you have.